So today we will be studying second order reaction and its half-life, and we will be discussing only one case today, which is when concentration of your reacting molecules, both the reacting molecules is same, or we can say when there is only one reactant giving us product but the order of reaction is 2. So the rate of reaction will become directly proportional to the concentration of reactant raised to power 2. In order to remove this proportionality sign, we write a rate constant K. Alright, now we also know that the rate of reaction can be written in the form of decrease in concentration of reactant with respect to time, or increase in concentration of product with respect to time. So here we are only considering the decrease in rate of reactant with time. So this will become equal to K into concentration term raised to power 2. Let's suppose this is first equation. Now by taking all the concentration term to the same side and remaining term to the other side, we'll get like this. On integrating it, now K here is a constant, so we will keep it outside the integration sign. Now this is something new. Okay, for solving this we will be using this formula. You must have studied this. Integration of x raised to power n dx is equal to x raised to power n plus 1 divided by n plus 1. This is this is the formula we will be using. So here what we have something similar to dx divided by x square. This you can write as x raised to power minus 2 dx. So if you have to solve this using this formula, what will you get? X raised to power minus 2 plus 1 divided by minus 2 plus 1. So you are getting x raised to power minus 1 divided by minus 1, and you can also write it as minus 1 upon x. So if we have to write the integration of a square with respect to dA, it will become minus 1 upon a. So we will be putting this value here. We have one minus sign outside, and by integration we are getting minus 1 upon concentration of A, and this becomes equal to KT plus your integration constant. Alright, this minus will become plus, so you will be getting 1 upon A equal to KT plus I. Now at initial time, that is T equal to 0, your concentration is A naught. By putting these values in equation 2, you will get 1 upon A naught equal to K into 0 plus I. Therefore I become equal to 1 upon A naught. Now putting this value into your second equation, you will get a new equation, that is 1 upon A equal to KT plus 1 upon A naught. This is your third equation. Now if you compare this equation is equal to as y equal to mx plus c, so this is a straight line equation, and if you plot a graph between 1 upon concentration of A with respect to time, you will get a straight line graph, and your intercept is equal to 1 upon A naught, and your slope is equal to K. So you will get this kind of graph. Now moving further, if we take KT on the left hand side and our remaining concentration term to the right hand side, our equation will become this. Now if somebody asks you the equation of rate constant for second order reaction, we will write it as 1 upon T alright. And if somebody asks you the equation for time, then we will rearrange it like this. This is your equation for time. Now comes the half-life. What is half-life? Half-life is the time at which the concentration of reactants become half of its initial concentration. So half life, if we have to find out for second order reaction, it is the time at which your concentration of reactant becomes half of its initial concentration. Alright, so by putting these values in our last equation, that last equation was T equal to 1 upon K into concentration of reactant at time T half. So we are taking time as T half, so we will be putting the concentration corresponding to that T half, that is A naught by 2. So A naught by 2 minus 1 upon A naught. On solving this, you will get 1 upon K, 2 divided by A naught minus 1 divided by A naught. What will be the remaining? 1 upon A naught. So our T half is equal to 1 upon K A naught. And we can clearly say our T half is inversely proportional to our initial concentration of reactant. Also,